What if the greatest danger of colonizing Mars is not that we fail to survive there, but that we succeed? Imagine a future in which human beings finally escape Earth, build cities beneath the Martian sky, and become a civilization spread across two worlds. It sounds like the ultimate insurance policy against extinction. But hidden inside that dream is a disturbing possibility. The moment humanity becomes a multiplanetary species, we may begin an experiment that has never occurred in our history. An experiment involving isolation, evolution, artificial intelligence, nuclear technology, planetary engineering, and population separated by millions of miles of space. And once that experiment begins, there may be no way to reverse it. Leonard Susskind has spent much of his career thinking about the deepest limits imposed by physics, black holes, quantum information, the structure of space-time, and what physical law allows or forbids. He is not known for arguing that Mars colonization will end humanity, but the physics he has helped illuminate gives us a useful way to examine one of civilization's most ambitious dreams. Because before imagining cities on Mars, we have to confront something far less romantic. Space is not merely empty distance. It is an environment fundamentally hostile to the human body. Mars sits on average roughly 140 million miles from Earth, although the distance between the planets changes dramatically as they orbit the Sun. With current propulsion technology, a crewed journey would likely take months. During that time, astronauts would live far beyond the protective environment most humans have experienced. Earth possesses something extraordinarily valuable that we rarely notice: a magnetic field and a thick atmosphere. Together, they help shield life from energetic particles arriving from space and from the Sun. Astronauts traveling to Mars would have much less protection. Galactic cosmic rays and solar particle events can pass through spacecraft and biological tissue, potentially damaging DNA and increasing long-term health risks. This is not speculation. Radiation exposure is one of the established challenges of human deep space exploration, and Mars does not solve the problem when the spacecraft arrives. Its atmosphere is extremely thin, composed mostly of carbon dioxide, and provides far less shielding than Earth's atmosphere. Mars also lacks a strong global magnetic field like Earth's. Anyone living permanently on the surface would therefore need substantial protection, possibly habitats covered by Martian soil, underground structures, or other forms of shielding. Already the romantic image begins to change. The first Martian city might not look like a futuristic glass metropolis beneath a beautiful red sunset. It might look more like a bunker. But radiation is only the beginning. Mars has about 38% of Earth's surface gravity. We know that prolonged microgravity can weaken muscles, reduce bone density, and cause other physiological changes. What we do not yet know is whether humans can remain healthy for an entire lifetime in Martian gravity. That distinction matters. Zero gravity has been studied extensively aboard orbital spacecraft. Mars gravity is not. No human being has ever spent a year living at zero. 38G. No child has ever developed under those conditions. No pregnancy has ever been studied there. We do not know whether normal human development, cardiovascular health, bone formation, or reproduction could proceed safely across generations. So imagine the first permanent settlers. They arrive believing they have escaped Earth's limitations. They build pressurized habitats, extract water from local ice, grow food under controlled conditions, and slowly become independent. Then decades pass. Children are born. Those children grow up in gravity far weaker than Earth's. What happens when they try to return? Perhaps technology could compensate for some physiological effects. Perhaps future medicine could address others. But it is also possible that people born and raised on Mars would find Earth's gravity extremely difficult to tolerate. At that moment, Mars would stop being merely a distant colony. It could begin becoming a separate branch of human civilization. And physics would enforce the separation. Light itself takes minutes to travel between Earth and Mars. Depending on the planet's positions, a one-way radio message can take roughly 3 to 22 minutes. That means there can be no instantaneous conversation between the worlds. A person on Mars cannot call Earth and receive immediate instructions during an emergency. Mission control cannot directly fly a spacecraft in real time during a crisis. A doctor on Earth cannot remotely control every moment of a delicate procedure as though standing beside the patient. Mars must learn to decide for itself. This delay sounds small until we imagine politics. Suppose a Martian settlement depends on Earth for critical equipment. Earth governments impose regulations. The settlers disagree. A message is sent. Minutes pass. A reply comes. Another message is sent. Minutes pass again. Now imagine that delay layered onto years of cultural separation, economic competition, and generations of people who have never seen Earth's oceans, forests, or cities except through screens. History offers a warning. Whenever human populations have become geographically separated, they have often developed distinct identities, political interests, languages, and institutions. Mars would represent separation on a scale history has never experienced. There would be no shared border, no road between capitals, no ship crossing an ocean in a few weeks. There would be millions of miles of vacuum. And then comes the deeper problem. A successful Mars colony cannot remain permanently dependent on Earth. If every essential component must be shipped from Earth, then Mars is not truly a second home for humanity. It is an outpost with an extremely long supply line. Real survival would require local production. Martian settlers would eventually need to manufacture structural materials, replacement components, electronics, medicines, tools, energy systems, and perhaps spacecraft components themselves. They would need agriculture robust enough to survive crop failures. They would need industrial systems capable of operating without constant rescue. In other words, to become a genuine backup civilization, Mars would have to become technologically powerful. And power creates its own risks. A civilization capable of transforming Mars into a sustainable home would command technologies far beyond simple rockets and habitats. Advanced automation would almost certainly be essential. Robots would mine resources, construct shelters, inspect machinery, and perform tasks too dangerous for humans. Artificial intelligence could become increasingly important because communication delays make continuous control from Earth impractical. This does not mean intelligent machines would inevitably rebel. There is no established scientific evidence that Mars colonization would produce hostile superintelligence. The real concern is simpler. A distant settlement operating in an unforgiving environment would have enormous incentives to automate as much as possible. When survival depends on machines, failures that would be inconvenient on Earth can become existential. Imagine an automated agricultural system malfunctioning. On Earth, food can often be transported from somewhere else. On Mars, the next major shipment may be months away. Imagine a software error affecting atmospheric controls, a pressure failure, a contamination event, a breakdown in water recycling. A settlement on Earth can survive many failures because it exists inside a living biosphere. Mars does not offer that luxury. Outside the habitat, the environment cannot sustain an unprotected human for long. Every breath becomes technological. Every glass of water becomes technological. Every harvest becomes technological. Human civilization has never before attempted to make an entire population dependent on engineered life support systems for every second of its existence. That creates a strange paradox. Mars is often described as protection against catastrophe on Earth. But early Mars settlements could initially be far more fragile than Earth. Even after nuclear war, asteroid impact, or extreme climate disruption, Earth would still possess enormous quantities of water, breathable atmospheric oxygen, accessible biological resources, and gravity to which our bodies are adapted. Mars begins with none of those advantages. To understand the scale of the difference, imagine discovering two abandoned houses. One has broken windows, damaged plumbing, and no electricity. The other has no air inside, almost no usable water, freezing temperatures, and walls that must never lose pressure. Which one is easier to repair? Earth can be damaged catastrophically. Mars begins catastrophically hostile. That does not make colonization impossible. It changes what colonization means. Then we encounter perhaps the most famous dream associated with Mars, terraforming. Could humanity transform the planet itself? Could we warm Mars, thicken its atmosphere, release trapped gases, melt ice, and eventually create something more Earth-like? The idea appears throughout science fiction and serious scientific discussion, but current evidence makes the challenge enormous. Mars does contain carbon dioxide in its atmosphere and in reservoirs associated with the surface and polar regions. But research using spacecraft observations has suggested that accessible carbon dioxide is insufficient with present-day technology to create anything approaching Earth-like atmospheric pressure through straightforward release alone. Even if future technologies found other approaches, planetary engineering would operate across extraordinary timescales and would demand immense energy and resources. And then there is the atmosphere itself. Mars has lost much of the atmosphere it possessed in its distant past. Without a strong global magnetic field, the solar wind interacts with its upper atmosphere, and atmospheric escape continues. So terraforming is not like renovating a house. It is closer to rebuilding a planetary system. Yet suppose humanity eventually develops technology powerful enough to do it. That achievement creates another uncomfortable question. What else could technology capable of altering an entire planet do? The tools required for large-scale planetary engineering would represent control over energy and matter on a level beyond anything civilization possesses today. The same scientific progress that could make Mars safer might also make civilization more dangerous. This is a pattern that has followed humanity for centuries. Fire warmed our ancestors and burned their enemies. Chemistry produced medicine and explosives. Nuclear physics gave us reactors and atomic bombs. Biotechnology can cure disease while raising concerns about engineered pathogens. Technology rarely arrives with only one possible use. The more powerful civilization becomes, the greater the consequences of both wisdom and error. This is where Susskind's world of theoretical physics becomes relevant in a deeper way. Modern physics teaches humility. Nature does not negotiate with ambition. A black hole does not care whether an astronaut understands general relativity. Radiation does not care whether a mission has inspirational goals. Vacuum does not care how advanced a civilization believes itself to be. Physical law is indifferent, and Mars would expose human beings to that indifference every day. But perhaps the most unsettling transformation would not happen to the planet. It would happen to us. Consider two populations separated for centuries. One remains on Earth, the other lives on Mars. The Martian population faces lower gravity, greater radiation exposure, enclosed habitats, restricted resources, and perhaps different day-to-day survival pressures. Natural evolution normally operates across long timescales. A few centuries would not automatically transform Martian settlers into a different species. But future humans may not rely on natural evolution. Genetic engineering could change the equation. If safe and sufficiently advanced gene editing technologies emerge, future settlers might be tempted to alter human biology to better tolerate radiation, reduce gravity, or other aspects of extraterrestrial life. This remains speculative. We do not currently possess the ability to redesign humans safely for Mars, but the incentive is easy to imagine. Instead of spending unimaginable resources making Mars more like Earth, future settlers
10,
might ask
9,
a disturbing question. Why not make humans more compatible with Mars? At first, the changes might be medical. Better protection against radiation damage, altered bone metabolism, improved tolerance to low gravity. Then perhaps changes become hereditary. After enough generations, Earth and Mars might no longer disagree merely about politics. They might disagree about what humanity should become. And unlike conflicts between nations, the two sides could possess fundamentally different relationships with their environments. Earth humans would inhabit a biological world. Martian humans might inhabit a technological one. Earth civilization could view Mars as an experiment. Mars could view Earth as an ancient civilization trapped by tradition. Now add distance, add resource competition, add different governments, add powerful technologies, add populations that may eventually consider themselves separate civilizations. Suddenly the phrase multiplanetary humanity begins to sound less like a single species expanding outward and more like the beginning of multiple civilizations sharing a common origin. Would that make humanity safer? Possibly. If Earth suffered an extinction-level disaster and Mars were genuinely self-sufficient, human civilization might survive. That is one of the strongest arguments for becoming multiplanetary. But diversification also creates new categories of conflict. On Earth, nuclear weapons can cross continents in minutes. Between planets, the mechanics would be different and far more complicated. Yet any civilization capable of routine interplanetary transportation would inevitably possess tremendous control over high-energy propulsion and objects moving through space. An asteroid does not need explosives to be dangerous. Velocity itself contains energy. This does not mean Martian settlers would weaponize asteroids or spacecraft. There is no reason to assume that future civilizations must become enemies, but physics creates possibilities long before politics decides whether to use them. Humanity discovered that lesson in 1938, when nuclear fission was identified in the laboratory. Within 7 years, nuclear weapons had been used in war. The underlying physics had always existed. Human knowledge changed what was possible. Mars would demand enormous scientific knowledge merely to survive, and that creates perhaps the central paradox. To make another planet safe enough for humanity, humanity may need to become powerful enough to threaten itself in entirely new ways. There is another mystery, however, hidden beneath the Martian soil. Life. We do not know whether Mars ever hosted life.
Liftoff.
Ancient Mars was very different from the world we see today. Geological evidence shows that liquid water once flowed across its surface. Rivers carved valleys. Lakes existed. Some environments may once have possessed conditions that on Earth are associated with habitability. NASA's rovers and orbiters have transformed our understanding of this ancient world. But evidence of past habitability is not evidence of past life. No confirmed Martian organism has been discovered, and that uncertainty matters enormously. Suppose humans arrive carrying billions of microorganisms. Despite sterilization procedures, humans themselves are ecosystems. Our bodies contain enormous microbial communities. Permanent settlement would inevitably increase the risk of contaminating Mars with terrestrial biology. If researchers later discovered microorganisms beneath the Martian surface, a terrifying scientific question could appear. Did we discover Martian life, or did we bring it? Planetary protection exists partly because contamination could destroy the integrity of one of the greatest experiments imaginable, determining whether life emerged independently on another world. And if Mars does contain an indigenous biosphere, even a microscopic one, the ethical problem becomes profound. Would humans have the right to terraform a living planet? Would spreading Earth's biology across Mars amount to exploration or ecological replacement? The answer would affect more than Mars. If life originated independently twice in one solar system, then life may be common throughout the universe. But if Earth remains the only world where we find evidence of an independent origin of life, the silence becomes harder to ignore. This leads toward one of the deepest puzzles in cosmology and astrobiology. The universe is approximately 8 billion years old. Our galaxy contains hundreds of billions of stars. Many stars possess planets. Some planets exist in environments where liquid water could potentially occur. So where is everyone? The question is associated with the Fermi paradox. If technologically advanced civilizations can arise and spread between worlds, why don't we see obvious evidence of them? There are many proposed answers. Perhaps intelligent life is extraordinarily rare. Perhaps technological civilizations do not last very long. Perhaps interstellar travel is simply too difficult to produce galaxy-spanning civilizations. Perhaps advanced civilizations exist but are difficult for us to detect. We do not know. But Mars gives the question an unsettling relevance. Humanity may be approaching its first attempt to move permanently beyond its home planet. If civilizations throughout the universe face similar moments, then perhaps the dangerous stage is not reaching technological intelligence. Perhaps the dangerous stage begins when intelligence becomes powerful enough to redesign planets, biology, machines, and itself. A civilization that cannot control those powers may disappear. A civilization that can control them may spread. We have no evidence telling us which path is more common, and Mars could become humanity's first test. Not because the planet itself is evil, not because exploration is reckless, and not because physics tells us colonization must fail. Physics tells us something more sobering. There is no guarantee. The universe provides possibilities, not promises. Susskind's work on black holes helped transform one of the great arguments in modern theoretical physics, whether information falling into a black hole is fundamentally destroyed. His long debate with Stephen Hawking became part of a revolution in our understanding of quantum gravity, leading physicists toward the view that quantum information must somehow be preserved. There is something strangely appropriate about applying that lesson to civilization. When humanity leaves Earth, what information do we preserve? Our science, our history, our languages, our institutions, our compassion, our conflicts, our prejudices? Mars would not receive an idealized version of humanity. It would receive us, every strength and every weakness. We often imagine Mars as a blank world where civilization can begin again. But humans never begin from nothing. We carry our past with us. The first Martian settlement could become one of the greatest achievements in human history, a demonstration that intelligence can cross the void, adapt, cooperate, and survive beyond the world where it evolved. Or it could reveal something darker. Perhaps civilizations are safest while their power remains smaller than the consequences of their mistakes. Perhaps there comes a moment when technology expands faster than wisdom. Nuclear physics brought humanity close to that boundary. Artificial intelligence and biotechnology may push it further. Planetary engineering could push it further still. Mars would not create these dangers. It would amplify them. And yet refusing to leave Earth carries risks of its own. Asteroids exist. Supervolcanoes exist. Pandemics occur. Stars change over astronomical time. Earth will not remain habitable forever. Hundreds of millions to billions of years from now, the increasing luminosity of the sun will profoundly alter our planet's climate. Far later, the sun will become a red giant. If intelligence is to survive on cosmic timescales, remaining permanently on Earth is not an option. So humanity stands between two kinds of risk: stay forever, and eventually nature wins. Expand too recklessly, and perhaps we destroy ourselves before nature gets the chance. That may be the real challenge of Mars. Not engineering, not rockets, not radiation, maturity. Can a species that evolved in small competing groups acquire planetary-scale power without using that power catastrophically? Can humans build a second civilization without reproducing every destructive pattern of the first? Can two worlds remain connected when physics itself forces them to communicate across an ocean of time? And if Martian civilization eventually becomes independent, biologically altered, culturally distinct, and technologically self-sufficient, will its inhabitants still look toward the blue point in their night sky and call the people living there their own? Perhaps the first person who steps onto Mars will not simply begin the colonization of another planet. Perhaps that footprint will mark the moment when human history stops being the story of one world. From then on, there may be no single center, no single civilization, perhaps eventually no single definition of human. And somewhere in that distant future, a child may stand beneath the pale Martian sky, look toward a tiny blue star that cannot be reached for months, and learn that every person who ever lived once belonged to that world. They may call it Earth. They may call it home. Or they may call it something else entirely. And if that day comes, the most important question will no longer be whether humanity managed to survive Mars. It will be whether the civilization that emerged from the journey still remembers what humanity was supposed to mean.